this video we'll be looking at another example of deformation due to axial loading. This is a unique example, so I'm going to actually write it down. Deformation due to axial loading, and this is more example. Okay, so this problem have a rigid beam AB, and it's supported by two posts, AC and BD, and looks like AC is made of steel and have its own diameter, and BD is different material, aluminum, and have larger diameter. And then there's a concentrated load, 90 kilonewtons applied at F, and they want us to know what's the displacement of point F. Yeah, so how do we figure this out? Now let's first thinking about this. If we were just looking at FBD of this beam AB only, just like how we look at the frame, we look at each member. We just here look at the AB. There's a 90 kilonewton right here, and at point A, there's going to be a supportive reaction there, and also at B as well. We want to find what's the support at A, and this is at B, and how do we solve that? I mean, this is quite straightforward, right? We can quickly get that information. Let's see. If I want to find support reaction at A, I'm going to do some of the moments at B. So I have A, this unknown, times this entire beam for the moment of arm. That's going to be 200 plus 400. That's going to be 600. And it's clockwise rotation, so it's negative. Then I have this 90 kilonewton. Moment of arm will be 40, and that's counter, so plus. That equal to 0. From that, what can we get? A will be equal to 60 kilonewton. If A is 60, we can quickly get B will be 30, right? Force at Y direction. So knowing A and B, how would that help us figure out the rest? Now I'm going to look at FBD number 2. If this is 1, FBD number 2, we're going to be looking at AC post, AC. So using this Newton's third law, for example, here you have a force A, reaction force at A is pulling this beam AB up. So beam AB gonna push in this post AC downward, right? And equal by the opposite of 60 kilonewton. And so that's going to be, of course, at C here you will have normal force or from the ground to be 60 kilonewton. Okay, then you can quickly do another FBD 3 about our BD post. Will be similar situation, BD, and since at B there's a reaction B at 30 kilonewton pushing up, so AB is going to pushing it downward at BD as 30 kilonewton, and of course at D is going to be grounded, supported by the ground with 30 kilonewton. Okay, so knowing that, then you know this too is perfect axial loading situation, right? AC is having its compression, so is BD having compression. If they have a compression, they're going to have a contraction. So we're going to figure out how much change of deformation. What's a deformation in AC? That's related to our topic, which is deformation due to axial loading. So delta AC is going to be PL over AE. That's our formula. And then if you cut anywhere between A and C, you know the internal force will have to be 60 kilonewton. And so that's going to be negative because it's compression, it's contracted. And L, what's the length of AC, which is this value, 300 millimeter. And area, do we know the area of AC? They told us AC has a diameter of 20, so which means it's going to be pi r, r will be 10 square, pi r square. So that's in millimeter square in area. And how about our elastic modulus? For A is made of steel and it's 200 gigapascal. Okay, so that's what we have. So that's how much deformation happens at AC. Now, well, the unit is a mess, but we are going to be smart about it. Let's think about it. What we learned before, we said if it's Newton per millimeter square, that gives us a unit of megapascal. And we also learned kilonewton per millimeter square, that's going to give us unit of gigapascal. So it looks like we're going to use this. So if that's the situation, gigapascal is essentially kilonewton per millimeter square. Then millimeter square cancel out, we'll get kilonewton. Then kilonewton cancel out. Then if I don't do anything, I don't do any unit conversion, I'm gonna get the units of millimeter because that's what's left. That's the deformation. That's not too bad, right? So that's going to be our delta AC. I'm going to put into calculator, so pause for a second. You're going to do the same thing. 60 times 300 and divided by 100, then divided by 200, and then divided by 3.14. And I have 0.286, 0.287 to be more exact. That's how many millimeter? Okay. Then we're going to do the same thing to figure out how about BD post. BD is going to be subject to shortening as well, but how much? It's going to be a different value, right? Why? Because they have a different internal loading. This is -30, and even though they have the same length, but they have a different area because BD is diameter 40, so it's going to be pi r square. R is 20 millimeter square, and BD is made of aluminum and has 70 gigapascal. All right, so we took care of the units before. If we don't change anything, we know we're gonna get millimeter. So put into calculator. So 30 times 300, then divided by pi, divided by 400, divided by 70. We'll have 0.102 millimeter. Okay, so that's how much contraction the deformation happens to this post. Now if we're going to draw that, so AC obviously have, okay, this is negative and this is negative. So AC used to be how much? 300 millimeter, and then it's gonna reduce 0.287. So if I'm exaggerating drawing this, so AC will be shorter, right? And BD will be taller because it contracted less. So that's going to be our AC. This will be our BD. Well, then we have this rigid beam AB on the top. The reason we call, they specifically said this is rigid beam, which means they won't gonna warp. They're gonna be continuous straight. It's gonna be like this. And our goal is to find out how much displacement happens at F. F is right here. So how do we figure that out, right? Used to be, this is gonna be after. If we draw before after, this is after, and before will be like this, right? And that's F there, and now has been, this is before. F is here now. If I'm drawing, overlay them together, so this is my after. This is my F now. I call F prime. Okay, so how do we figure out the displacement, which is from F, original, final? That's our displacement. How do we figure out that distance? Well, it's pure geometry, right? So let's go ahead and try to solve it. If I were trying to look at that top shape right here, this area. So we isolate that out, and this is how much reduced contraction happened at the BD post. We know it's 0.102. And this is how much contracted at AC post. We know it's 0.287. And F is here, and we know it's 200 and 400. So go back here. This is 200 millimeter and 400 millimeter. Looks like all those units is in millimeter, okay? And our goal is to finding out that yellow line. Okay, how do we solve that? We're going to draw some supplementary line to help us solve that. If this is 0.102, can you tell me what's this length here? Would that be 0.287 minus 0.102, right? Which will give us 0.185. So knowing that, I know I want us to focus on this triangle area. Now we're going to use proportionality or similar triangle, whatever you call it, and to set up our equation. And our goal is to figure out this length first, right here. So that purple one, okay? Then that purple one divided by this length, 0.185, this length, is going to be equal to this length, 400, divided by this entire length, 600. So we will be able to figure out this question mark, the purple one, how much that is. So 400 times 0.185, then divided by 600. I have 0.323 repeating. So knowing that, we want to find this entire length, this one here. That would be the displacement, right? What you're trying to look for. Displacement of F, that would be equal to this question mark, you figure out 0.323 repeating, plus this length right here, which is same as here, 0.102. And then we will have 4.425. I feel like this number I did is not correct. You probably already caught it before I realized. So let me try one more time. 400 times 0.1 400 times 0.185 divided by 600. Yep, I don't know where I got it wrong, but it's not that. 0.123. So knowing that, I'm going to go ahead and change. This is 0.123, and then that will give us a different number. That will be 0.225. That's more like it. So that's how much displacement at F. Okay, so that's wrap up for this problem. And this is a very kind of unique way to embed deformation due to axial loading. And you might see some of those in your homework or FE exams. All right, I'll see you on the next time. Bye now.